Consider a setting here where we are doing a Poisson approximation. We're letting all these random variables be independent rare events. And we have many of these rare events. That's what n large means. And then we're setting the probabilities of each of these as small for all of these j's. And then we define x as the sum of these indicator random variables. And we're also letting lambda be this expectation of x. First we ask to find the MGF of x, and then we're going to approximate whatever we get from this A in the following format and see what that yields. Okay, so let's start by finding the MGF of x. The MGF of x, by definition, and the first inequality is this expectation over E of t of x. In the second inequality, we're going to unpack x and then let's see what that gives. Well, e to the t x is basically all these random, these indicator random variables. So that gives I, stands for indicator, a1 plus all the way up to indicator a n. Okay, and now we know that all these indicators, they are IID. So that's what we're going to do here, and that means that we could utilize, can write the exponential in the following format: J. I'm going to write it, let's do this correctly, all the way to E expectation e to the t I a n. Independence allows us to unpack this x in the following format. Alright, so what is now the next step? Well, we know that all of these random variables, each of them have different probabilities. Well, yeah, so we can do several things here. We could find, let's do the following. Just going to move down this equality and then figure out what the expectation of one of these guys are. Okay, let's do it here on the side. The expectation of one of these, and it will be analogous to all of these, is that we have a Bernoulli trial here, right? It's one event happening with probability P1. So the expectation of this event is basically then writing out all these possible events, which would be 0. So when we have the variable here, let's see here, when this variable here is 0, so when this event doesn't occur, we have e to the t becomes 0. So let me just, for the sake of clarity, just write it out like the following. So we have P1 e to the t x, and then we have, so this is when x will be x equals 0, and then we have when the complement, which is 1p minus 1, is e to the t, also x, but now when x equals 1. My bad, this should be in the other direction. This is when x equals 1, x equals 0. Because x equals 0 is the complement, P1 is when it actually occurs, when x equals 1. And this then simplifies to P1 ET plus 1 minus P1 and x times T0 is just 1. So it's e to the 0, so it becomes 1 here, okay? And now we have, notice that we have different probabilities for each of these events. So P1 will have, obviously, A1 have P1, A2 has P2, IN has Pn. So we have to then, we write it out in the, and we're multiplying all these. So we're taking multiplication from I equals 1 to n P to I ET plus 1 minus P1. That is the MGF of X. And notice this is as simplified as it can become at the moment, because we have different probabilities. Moving on to the next question, we are now going to approximate this quantity. We are asked now to approximate it in the following format. And as it said, as it is written here, x is very close to 0. This is a good approximation, otherwise it's not. Okay, so let's move on here to the next thing and say, all right, so how do we do this? Well, let's start by just copying this piece here. And now we are given, I'm going to move it down here. We're given the following, that 1 plus x is approximately e to the x, especially when for x small. So let's see if we can get this term, well, these terms here in the following format, and see if we can rewrite this whole thing in terms of this. That's our strategy. So let me just do it for the sake of simplicity by just writing it out like the following. Doing like this. So we have P I E T, and by the way, this should be an I here. It's the same thing as we're just opening up this parentheses. So we have minus pi plus 1. We then can factor out pi e to the t minus 1 plus 1. Now this pretty much looks like this thing here, where x is all of these terms here. So this is x. Alright, so we can now write it out like the following. So we're going to, just for the sake of seeing what is going on here, let me copy this, duplicate, like the following. And right now this is not an inequality anymore, because we're going to utilize this approximation here. And so that is, well, just said not write inequality. It should not be inequality. So 1 to n. And here we basically now have e to the x, e to the x. And x now is pi et minus 1. That is our approximation. And now in the next step, we're going to figure out if we can simplify what is happening in the exponent of e. And thinking about what is happening in this multiplication here. So let's just write out the whole expression in the following way. So we have p1 et minus 1, and then we have plus all the way up to pn et minus 1. And that now is, let me continue here, we can now factor out et minus 1, so that et minus 1 to all these p sums. So these are now sums, p I to n like that. And this, in fact, this term here is in fact lambda. And that might be a little unclear to see how that term becomes lambda. So let me just show you what assumptions that is based on. It's based on the Poisson approximation. But let me continue ahead. Let's do the following. I'll do the following. So let's continue this calculation up here or down here. So we have the sum of I1 to n pi. Okay, so that is the same thing as the sum over in as the probability of the event AI, right? That's just given in the information over here. Now I'm using a different index here, I realize, but that's okay. And because these are Bernoulli events, these A's, we can use the fundamental bridge. The fundamental bridge says if this term here is Bernoulli, it's the same thing as the expectation. It's the same thing as the expectation of the indicator of AI happening here. Okay. And then the next step, we just use the linearity of expectation in the reverse so that we can move it out of the sum. I1 to n. Now we have all these indicators like this, and this whole thing. We're taking the expectation over this whole thing. Now, we also defined all these terms inside here. Well, sorry, this whole sum as x. So, and that was given in the beginning here. Let x equals all these indicators. We're using this information over here, and then we're getting now almost done here. The expectation over. Well, this is getting a little ugly. Sorry about that. Ex sum like this, and now by the Poisson approximation, says that this random variable x inside here is approximately distributed Poisson lambda. And we also know, let's take another color just to highlight that we are commenting this term. And we also know that the expectation of a random variable Poisson is indeed lambda. So this is now lambda. And therefore we're getting this lambda from this sort of derivation here. Okay, so and now we are basically done here. So we have expectation over lambda e to the t minus 1, and that is what we were asked to show.